Okay, I need to do it very quick. So here for this structure, okay, plus proton, right? And proton prefer to attack here, right? Because if proton attack this carbon, you will get the positive charge here. You get a primary carbon cation, and only proton attack here. Then you will get a like that, right? The thing is that there's a, so there are two ways. One way is that for this carbon, the whole group move to here to form tertiary carbon cation, right? Or the hydrogen from here moved here. And then here the positive charge, there are two ways. But in chemistry, always choose the easiest way. Always choose the easiest way. So you will get a tertiary carbon cation like that. Because tertiary carbon cation is more stable. It's more stable. And then the chloride, the negative chloride will attack here for the compound E. Okay, compound E. And then question 7. Question 7. Question 7 is what? We discussed this. Is hydroboration oxidation reaction is what? It's cinder addition and anti-mark, right? The cinder addition and mark. So the added hydrogen and the hydroxy group should be syn 6, right? Should be 6. Okay, should be 6. And then it's anti-mark. Anti-mark. So the answer should be E. Why is that? Because first, anti-mark. Anti-mark means the proton will attack here. The proton will attack the carbon with less hydrogen. So the proton will attack here. And the hydroxy group will be here. At the same time, hydrogen and hydroxy group should be syn, should be cis, should be on the same side. And only this, because only this is correct. Why? Because if this is behind the plane, then another hydrogen must be out of plane. And this is out of plane, this is out of plane. They are cis. They are cis. And then there's another possibility, this hydroxy group is behind the plane. And then this hydrogen is behind the plane. They are enantiomers. They are enantiomers. So the correct answer should be E. It's anti-mark and it's cinder addition. The added hydrogen and the added hydroxy group should be on the same side. On the same side. So if you look at question 8, question 8, 6, 2-pentane. Question 8, I'm sorry. 1, 2, 3, 4, 5, 2. I'm sorry, C's. Okay, then we go this. Okay, and then we'll cold alkane. So after the addition, these two hydroxy group should be like that. So these two on the same side, and this hydroxy group, two hydroxy groups should also be on the same side. Then we can determine the chirality. Or here, chirality here, and then we can find the one that have the same chirality for these two carbons. Oh, there's another possibility, I'm sorry. Another possibility is like that. So they are enantiomers. Okay, they're enantiomers. Because yeah. So we first need to figure out the chirality, and then we figure out the chirality here. We need to figure out chirality, and then if they match, then we choose that one. So the answer should be A, equal amount. Why is equal amount? Because it can be two of them. It can be C's, can be C's. There are two possibilities. Okay. For question 9, we discussed this, right? Is what? Is halohydrin, right? So halohydrin addition. And in this reaction, chloride is positive here, and OH is negative, and is marked addition. Is marked addition. Marked addition. That means the positive chloride should be added to the carbon with more hydrogen attached. Yeah, and then question 9. Question 9. Okay, if you look at question 9, the structure is like what? Question 9. So this double bond is here, right? Double bond is here, and is marked addition, meaning the positive chloride will be added to this carbon, right? Because this carbon has, first there's double bond. This carbon has 2 hydrogen here. This carbon has only 1. 0. So the positive chloride should be added to here, and then the OH group should be added to here. And the answer should be E. None of them is correct. The answer should be E. That is marked addition. It's in water, remember? If it is chlorine in carbon tetrachloride, then it should be, the 2 chlorine will be added to this double bond. But if it's in water, then chloride is positive. Why? Because if you compare the electronegativity number, chlorine has lower electronegativity number. Chlorine 3.0, oxygen 3.5. So when they form a compound, this hydroxide should be negative, chloride should be positive, and it's marked addition. So the answer should be E. None of them is correct. And for question 10, you can find the slide. You can find the slide. This is ozone. If when we use this to oxidize the alkene, we'll get what? We'll get either ketones or aldehyde. Cannot go further to carboxylic acid. So it should be break here to form this 1 carbon here, right? Then it should form this. And this one, the same, will form. So the answer should be D. The answer should be D. Ozone cannot oxidize to carbonic acid, can only oxidize to ketone or aldehyde. So question 10 is quite straightforward. So this oxymercuration, demercuration, right, is what? Is marked addition, right? Is marked addition. Is marked addition. So, well, then because we have limited time. So for this structure, we discussed this quite a few times in class. And if you look at here, in the class we discussed this, right? If this is OH group, if these both OH groups are out of plane, then there is a mirror plane. So there's a plane, symmetrical plane here, right? There's a symmetrical plane here. Then, you see that? There's a symmetrical plane here. this side, this half, and this half are the same. When they have a symmetry plane, it's like this. Like this. They must have opposite chirality. Okay, opposite chirality. And then now, for this question, it is behind. Then these two carbon must have the same chirality. We don't need to figure out, right? Well, I think there's only one of them. Only C tells they have only C. You see, only in C, the chirality of these two carbon, these two chiral carbon are the same. Because you see that if both of them are out of plane, if both of them are behind the plane, there's a symmetry plane. There's a plane of symmetry there. And you can see half here are exactly the same. In that case, they must have opposite chirality, like our hands. This is overlap. Because there's a mirror plane here, they overlap with each other. When they can look the same, then they must have opposite chirality. But here, one is out of plane, the other is behind plane. They must have the same chirality. They must have the same chirality. So only C is correct. Only C is correct. And then I think let me see. Actually, I discussed in this class. I discussed this in the class a few times, so I will discuss one more time. And then, if this is both, they must have opposite chirality because there's a plane of symmetry here. If this is R, this must be S. And then if you can take a look at this one, this is behind, and this is or behind. Right? If you draw like that, again, there must be a symmetry plane. And then, so this is S, this must be R. And this is R, this must be S. They are the same compound, right? We discussed this. They are the same compound. You don't look at the drawing, you look at the real thing. The real thing, we can only determine this from the chirality. This SR, this is RS. They're the same thing. They're the same thing. And for question 13, so this is question 12. For question 13, I need to. Question 13. For question 13, okay. So suppose it's like that. Suppose this. Then we can see there's a symmetry plane, right? There's a symmetry plane. And then these two carbon must have opposite chirality. At the same time, these structures are symmetrical. Therefore, they have opposite chirality. Therefore, the chirality of these two chiral centers cancel. Then it is a methyl compound. But if you replace this methyl group with OH, not a methyl group anymore, but the OH, they still have opposite chirality, but the chirality cannot cancel because it's not a symmetrical structure, right? If this is methyl group, this is methyl group, then it's symmetrical. But if this methyl group is replaced by hydroxy group, then it's not symmetrical anymore. It's not symmetrical anymore. So, but they must, the symmetry cannot be cancelled. Okay, the chirality cannot be cancelled. It's different from that case. Even though they have opposite chirality, but the chirality cannot cancel because there is not a symmetrical structure. It's not symmetrical structure. Okay, so the answer should be, let me see, the answer should be enantiomers, right? Because they're just opposite. But for these two, they are the same compound. For these two, they're the same compound. Why? Because the chirality cannot cancel, or they can be cancelled. And the chirality for these two shown in the question cannot be cancelled because the structures are not symmetrical. But for this structure, they are symmetrical. They can cancel each other. Okay, today we'll move on to lab 3. Lab 3, we discussed this in the class, right? We discussed this in the class. Williamson ether synthesis. And then, let me see. Yeah, we'll run a reaction here. So, yeah, we'll run a reaction in the hood. But yeah, just in case. Just in case. Any questions? Because we need to be quick. Well, now you can have the exam paper, but you need to turn in before you leave today. Okay. And you can turn in here.